Hello students, in this video we'll see an example of solving a temperature problem on a disk using conformal mappings. Let's consider the temperature problem, the state temperature problem. Laplacian of U is equal to 0 on the unit disk. And on the top hemisphere, so U on the boundary, U of e to the I theta, is going to be equal to, 10 when theta is between 0 and pi. It's going to be 0 when theta is between pi and 2 pi. Like that, okay? So this jump temperature distribution. So in other words, what we have is the following. We have the unit circle. There's a unit circle. We want a harmonic function inside here. I want the temperature on the bottom to be 0. So there's no temperature over here. U is equal to 0 over here. And on the top, I want the temperature to be 10. I'd like to solve this problem over here. U equals 10 over here. That's the problem, okay? Now what we're going to do is we're going to use conformal mappings, right? So recall, if I want to solve Laplacian U equals 0 on a region R, with U equals B on the boundary of R, then what we can do is we can find the map F that maps R into S, conformal map. And then if I solve this problem over here, Laplacian of W is equal to 0 on S, and I want W to be equal to B compose F inverse on the boundary of S, then the function U, which is what? Well, I have a function on F. If I look at W composed with F, this is going to be what? This is going to be harmonic, because the composition of a holomorphic function, in particular conformal, with a harmonic function is still harmonic and has the right boundary conditions. Okay, that's my scheme. And so what we're going to do now is I'm going to find a conformal mapping of this disk onto another region that I can control. Okay, so how am I going to do that? Well, let's consider the following mapping. Let's map this via phi of z, which is I, and then 1 minus z over 1 plus z. Well, what's going to happen over here? If I plug in 1, I go to 0, right? If I plug in negative 1, I go to infinity. Good. I go to 0 and infinity, right? And if I plug in I over here, where am I going to go? Well, if we plug in I, we're going to see exactly what happens over here. But what's the key feature of this? When we plug in positive real numbers over here, from this function, if points in the upper hemisphere over here, like I, for example, let's plug in I and see what happens actually. What would phi of I be? Phi of I would be I, 1 minus I over 1 plus I, multiplied by 1 minus I, 1 minus I. That's going to give me what? Well, the bottom is going to give me a 2. We have an I in front. 2I in front. It's going to be I. And then we're going to have a 2 in the denominator. And then we have a 1. And then plus I squared is negative 1. Then we're going to have a what? We're going to have a negative 2I, right? And so that's going to be a 1. Great. So when I plug in phi, I go to 1. So it looks like when I plug in 0 over here, I'm mapping to I. That's good. So what am I doing? So we have a couple of different points. We plug in z equals 1. Z equals 1 over here is going to go where? So z equals 1. When I plug in z equals 1 gets mapped to 0, right? That's phi of 1, right? When I plug in phi of I, where do we go? When I plug in phi of I, we get mapped over here to 1. Great. And so what's happening over here is mapping this upper. When we plug in, of course, negative 1, where do we go? When we plug in negative 1, we go to infinity, right? So it looks like this upper, this heated portion is going over here, like that. When we plug in 0 to this, we get to I. So if I plug in 0, 0 gets mapped over here to I. Let's look at the bottom hemisphere. What happens when I plug in negative I, for example? So if I plug in negative I, what's phi of negative I? By the same calculation, it's going to be I, and then it's going to be 1 plus I over 1 minus I. Hit it with 1 plus I, 1 plus I. And that's going to give me I times what? That's going to give me I times the bottom is going to be 2. The top's going to be what? 2I, and then the real terms cancel out, so I have a 2I, right? So I times I is negative 1. So this point over here, this cool point down over here, gets mapped where? That's phi of negative I. In other words, the cool region's being mapped over here, right? And then the hot region's being mapped over here, and everything else in the interior of the disk, right, is being mapped over here, right? Okay? So now what can I do? So now I'm going to consider the following harmonic function. Consider the function over here in this space over here, 10 over pi, and then pi minus the argument of w. Okay? Good. Well, what's this function over here? This function is a harmonic function. This is a harmonic function in the UV space. Moreover, what do I know? If I plug in any value on the real axis over here, that's u and that's v, right? Well, what's going to happen over here? What's going to happen is if I plug in a positive point over here, the argument is 0. So I'm going to have what? I'm going to have 10. Oh, it works. In other words, this harmonic function over here is what value? It's equal to 10 over here. And if I plug in a negative value, the argument's negative, right? So the argument's going to be pi, right? The argument over here is going to be pi. Pi minus pi is 0. So it's going to be what over here? It's going to be 0 over there. So this is a harmonic function in the UV space, and it satisfies the correct boundary condition. So call this thing over here. Let's call it what? Let's call it zeta of w, right? Satisfies zeta on the positive real axis, r plus, is going to be the value 10, and zeta on the negative real axis is going to be 0. So it satisfies the right boundary conditions. And so now we can construct our function, right? So now construct our solution. How do we construct our solution? Well, I know what w is. W is 5z, right? So our function is going to be what? Our function u of x and y is going to be what? Is going to be 10 over pi, and then pi minus the argument of 5z, okay, which is 10 over pi, and then pi minus the argument of I, and then 1 minus z over 1 plus z, okay? And now, of course, I'm out of space, but the whole point now is this is a relatively elementary calculation now. The whole point now is that we replace z with x plus iy, right? And then the argument, remember that the argument of this complex number, right? So the argument is going to be the ratio of the real and imaginary parts. So there's a little bit of a calculation to do, and then calculate, and then everything is in terms of x and y. So in other words, I've written this as u of xy, and I claim that really this is u of xy, right? Because I can replace z with x plus iy, and the argument is the ratio of the real and imaginary parts, right? Or call it the argument of a complex number, just x plus iy. It's just the what? It's just the inverse tangent of y over x, right? And so in other words, this is going to be replaced with what? We're going to replace with tangent inverse. And that will give us our harmonic function, and that solves the Dirichlet problem on the disk with a boundary condition that is equal to 10 on the upper hemisphere and 0 on the lower hemisphere. So it's a very standard sort of problem when you have these sorts of like jumps. When you have a jump, the best types of functions to look at are functions of the argument. Because what does the argument do? The argument jumps from 0 to pi as you go along different branches of the real line, right? So in other words, that's a very good, very standard approach. If you ever have a piecewise defined function on the boundary, look to the argument and look to conformal mappings. Thank you very much.